Hello everyone, welcome back. So today I'm going to be teaching about lower and upper bound theory. Before I do get started on this video, I would recommend watching last video called asymptotic notations. Reason being, it just might make more sense when learning about this topic, as some things that which I say today were covered in the last video, but if you don't watch it, I mean, that's fine as well, but I just recommend watching the last one. But anyway, back to today's video, we're learning about lower and upper bound theory. And I'm going to go further about theorems and all that stuff, but whenever we're just generally talking about lower and upper bound, then these are the definitions right here. In simple terms, we would call lower bound basically, part of our time complexity or algorithm, which is less, right? So that's where the term omega notation comes in. If you watched the previous video, you know that omega notation is what we call lower bound, or a time complexity which an algorithm which doesn't take much time. Upper bound is exactly opposite of that, right? That's where the name big O notation comes in. Basically, this is an algorithm which takes a lot of time. And then, we have these fancy words representing these constraints or constants, but this is just basically the general idea of lower and upper bound theory. Now we are going to the lower bound theory, and all basically which the lower bound theory states is that whenever we're talking about lower bound theory, there's something called Ln, and this basically represents the minimum. So basically, the theory is saying that it's not possible for any algorithm for a common problem cannot have time complexity less than Ln, right? Yes, lower bound theory, it takes less time for algorithms to run, but when there has to be some minimum for that to happen, and that minimum is represented by Ln. Then the second part basically states that even, in upper bound theorems, there is an Ln, which makes sense, because the Ln just goes higher than that. But Ln is present in both lower bound and upper bound whenever we're discussing. However, there are two examples of this theory. One is what we call tribal bound, and the second one is what we call computational model. So basically, tribal bound would be used in order, tribal lower bound, should add lower right there. But the tribal lower bound would be basically that we compare the number of inputs given and compare it to the output given. So in this case, an example would be, I'll just quickly erase this, just know this said computational model. But an example would be, so if for our input, I give two matrix of, pardon my handwriting, of 2n squared, n to the power of 2, not 3, 2. And this is my input, right? But my output ends up being one matrix of n squared. And that happens by n times n in order to get the output of n squared. That's my output. then when we compare our input and output, our output is less than our input, making this a perfect scenario of tribal lower bound. And we figured out this was an example of a tribal lower bound by comparing our input with our output. So that's an example of a tribal lower bound. Then we have computational model. So the thing with computational model, it's not that easy to find it with our input and outputs. We have to use comparison. And what I mean by that is, suppose if we want to find which one is more, takes less time, which algorithm takes less time, between maybe linear search and binary search. So I will list some numbers here. So for both scenarios, we'll just keep the same numbers. But the way we will get a number is different in both scenarios. So let's say in both scenarios, I want to get number 6. Then in linear search, remember in both these searches, the numbers have to be sorted, meaning that they have to be organized numerically. So it couldn't be that 3 is over here and 1 would be over here. No, it has to go from lowest to highest. But let's say I want to get the number 6 in both my instances. In linear search, I have to go through every single number. So I'd go 1, 1's not my number. 2, 2 is not my number. 3, 3 is not my number, and so on till you reach to 6. Whereas binary search is different. Binary search is like, okay, go to the midpoint of your numbers, and that would be right here. And is your number higher than 3 or lower than 3? Be like, it's higher than 3. Then we'd only deal with these numbers. And then it would take the middle of this one. So it would be 5. And is your number higher than 5 or lower than 5? My number is higher than 5. Is your number 6? Yes, it is. So we can see that when we went through our steps, in order to find 6 here, it literally took us 6 steps. Whereas here, we just found the middle of this once, then we took the middle of 5, and then we're able to get 6 in 3 attempts. So, that 3 was wacky. In 3 attempts, right? So that was literally half of the linear search. So whenever we're comparing these 2 instances, then we can clearly see that binary search would be a perfect example of lower bound. But one thing I do want to mention is that in here, in linear search, it took us 6 steps to get 6 times to get the number 6, whereas in binary search, it took us 3. So we would n would equal 6 in our linear search, and n would equal 3 in our binary search. And the reason why we're saying n would equal that, because n is the number of steps involved in order to get your result. And this is what these figures represent. So thereby, this is what the number n is equal to. But that's pretty much it for computational model. But another example of another part or theorem of the lower bound theory can be seen with the straight line and algebraic program. So here we have our straight line program, and we can see it's quite a simple piece of code, right? Basically, 2 parameters, A and B, are mentioned, and basically variable C is created, which adds these 2 numbers up. So whatever arguments you pass in, 5, 3, it would sum up to be 8. So this program, it's quite simple. So you could tell that it doesn't need much time in order for this algorithm to run and give, an output. But the same cannot be said of this algebraic program. And this is actually a formula of algebra. not only does it take 4 steps, right? Much more steps than this one required, but we also have to keep in mind that ax to the power of 2, which basically is represented like that, it has a degree. It has a power. So this makes this program run much slower. That leads us to a theorem. Basically, in order to prove that the optimal of solving an n-degree polynomial is O n. So the thing with this is that this program is currently big O n to the power of 2. So if you watched the last video, this is big O notation, which means it requires more time. And we don't want that. We want, as much as we can, we want that lower bound. So in this part, proof is that the best solution for reducing the time and make this problem less complex, we can divide the polynomial into several straight line problems. So we can create more of these, right? Because instead of multiplying v multiple times, we can maybe create a more efficient program. And we can do that. This code is a perfect example of that because we created a loop. Basically, for those of you who do not know what a loop is basically something that we program in coding, and it basically helps us iterate multiple times. So if I want to say hello 100 times, instead of writing 100 print statements, I could just create a loop and it would do that for me 100 times. And this is what we can see here. We created the same algorithm and implemented it here. It doesn't matter if you don't know how to mathematically solve this problem, when you could just see by the number of steps reduced. This, if we exclude the return statement, is only one step, but the loop runs it efficiently and we're able to do this, iterate it multiple times, making this able to support this theorem, and we're able to do this and it reduces to O n. And O n is much, much more lower than O n to the power of 2. So that's it for today's video of lower and upper bound theory. I hope y'all enjoyed and learned, most importantly. And yeah, to see y'all soon.